Okay, so these are the different surfaces we've talked about. Paraboloids. So this paraboloid, where's its vertex? 0, 0, 0, right? We know what it's like if you shift it to have a new vertex and you translate the whole thing. We know how to make, is it circular or elliptical? Circular, what would make it elliptical? If you had like a coefficient, like ×2 or divided by something or ×2, that stretches or smushes it on that axis. Okay? So then what's the difference between that and this? And remember what the traces were? So what were the z traces? So horizontal traces were what for this thing?
Circles.
Remember, if you set z equal to different constants, each time you set z equals to a constant, you get a circle. X squared plus y squared equals a number, right? That's a circle in the plane of that constant. And so then we saw what we saw these. So we had the point there, and we had these circles. As you increase z, we had these circles in horizontal planes. Z equals 4, z equals 9, z equals 10, z equals 12, and that kind of form a skeletal of the paraboloid. Just kind of like the tip of a rocket ship or something like that. But that keeps going on forever, right? All right, so what happens if you do horizontal traces of this? Do you get circles again? You get circles again, right? But obviously it's going to be different somehow. So what's different about this now? What's that? What about negative z's now? They're okay, right? So negative, if you can put a negative z, and that'll be okay because you'll get a positive z squared and you'll have a circle down there. All right, so as z increases, we're going to have what? Increasing radius of circles. And as z decreases negatively, we'll have increasing radius of circles. Okay, so there's still circles. But now, how does that radius increase with z? Right? So z is the radius now, right? If it's z squared equals x squared, then z is the radius. Whereas here, z was not the radius, right? Z was the radius squared, right? If you said z equals 5, then radius squared equals 5. Well, now if z equals 5, then z is the radius. So how does radius increase with z? If z is the radius, then radius is increasing how with z? The same, right? Or yeah, proportionally, right? So now you have the radius, as z increases, the radius of these circles increases proportionally, or at a constant rate, right? At a constant rate. So then how does that make this shape different than this? Yeah, so it's like the radius of the circle is like linear with z. And so then what kind of shape do you get? I already told you. Yeah, so now it's a cone because it's like cones have this linear sides, right? These linear sides rather than parabolic sides. So paraboloid, it opens as a parabola. A cone opens linearly. This is a crash course of cones. I usually have you guys work out some traces and do this, but don't have time. So, but we need to know about cones. So it's like the worst oval cone I've ever drawn. Okay, but you get the idea. So you still get circles for your horizontal traces, but now those circles grow linearly with z, and so then you have this lateral edge that's a straight line. And that makes a cone, and then the fact that it's a double cone is because z could be -2 and you get valid circles. So these are our key, and these are all in the second test too, but in the form of functions, right? So now we're going to start talking about functions in R3. Functions are, one type of function in R3 are surfaces, and so we're going to see all these again when we talk about functions in a couple days. Spheres, paraboloids, planes, cylinders, ellipsoids, double cones. So there's a lot of memorization aspect to this. You have to be able to look at an equation and know which one it is. You have to be able to look at a graph of one and identify what it is, and maybe given some elements of that graph, could you come up with the equation? Okay. Question?
With this, does it matter if there's negatives and positives in that cones? Like if it was c squared equals x squared minus y squared?
Oh no, so that will be different. If you don't have this exact pattern of the positives and negatives, you get something different. So if you have c squared equals x squared minus y squared, that could be some kind of weird hyperboloid. It's like something weird. And so we won't, you may see one once in a while, but you're kind of not responsible for it. So this is enough. This is enough here. These are the ones we'll see the most. We'll kind of, but yeah, just know if you change the sign on x squared or y squared, then yeah, you're getting something different. Something going to have parab. You know, we could do the traces. So given anything else besides these, if you make the traces, you could come up with some kind of shape of it. Yeah. But these are the ones you kind of have to memorize by recognizing their equations. Anything else you could build through traces. Does that make sense? Okay. So let's talk about vector functions. So vector functions, and I should really qualify here. One type of, because we were going to find out throughout this course, we're going to see many different types of vector functions. So here's the most basic one. An R3 vector function is this form. That you get a vector of x, y, and z components where each of the x, y, and z component is a function of some other variable. So x is a function of some variable t, y is another function of that same variable t, z is still a third function of that variable t. So what is this kind of almost exactly like that you've seen before? Yeah, parametric function, right? Parametric function. So we're saying is you just take it out of vector form and you write it as three equations and you have exactly what we've talked about in the past in Calc 2 as a vector function. We've already seen one vector function like this. What have we seen? That's a vector function just like this in this class. Lines fit this form exactly. So lines specifically, what did we have? We had, so it was like x naught plus at, right? Y naught plus bt and z naught plus ct. And we saw that x naught, y naught, z naught was a point on the line and abc was the vector parallel to the line or the direction vector. So now we're just getting broader. We're saying it doesn't have to fit that form anymore. If you let that form just be any functions of t, then this is what we're going to call our first vector function that we're looking at. Okay, so the domain, so the input of this is t. So as a function, we have input and output, or independent variable and dependent variable. So the independent variable here is t. And is that a scalar or a vector? Scalar. We have a scalar. In this type of vector function, we have a scalar independent variable, meaning a value. And then what is the dependent variable? What kind of thing do you get dependent? You get a vector. Okay? That's why it's called a vector function, because the dependent thing, the thing that comes out, is a vector. So independent scalar. So a scalar, in these kind of functions, a scalar is indicating a vector, right? According to these equations, f of t, g of t, and h of t. So the domain is all values of t that result in a valid vector. So is it all values of t that make all of the components defined or any of the components defined? It's got to make them all defined, right? It's got to make them all defined. If one of them isn't defined, then we don't have a valid vector. So that every value t that gives you a valid vector r then is in the domain. So it's kind of like the domain problems you used to do for checking functions for their domain. Now you have to do it 3 times, right? You've got to get the domain of this one, and the domain of this one, and the domain of this one. And then what will the domain of the vector function be? The union or the intersection of those domains? Intersection, right? It's going to be all the values of t that are in all three domains, right? So you have three domain questions to do, and then you're going to the intersection of those three will be all values of t that give you a valid vector. Okay, so that's kind of the nuts and bolts. Let's talk about visually how do these graph in R3, right? So it's, we've got what kind of is an R3 vector, so it's going to make some kind of graph in R3. Let's take a look at that. Way here. Okay. All right, so here is a vector function. X equals cosine t, y equals this polynomial, this quartic polynomial, and then z equals 0.5 sine of 5t. So here I'm showing t equals 1.4. So when you take t as 1.4, and you put 1.4 into these three equations, you get a vector, right, with x component, y component, z component, and then now this is showing that vector. Okay, so given the t value 1.4, you get a vector. And so now I'm showing that vector as a standard position vector, right, with its tail at the origin. Okay, so then what happens if I change the value of t? Simply, here's t equals 2.98. Here's t equals negative 0.46. So every time you put in a different t value for this vector function, you get a different vector. So the independent variable is varying t, and then the dependent variable is varying vectors. So what happens is we want to think about continuously changing t, right? If we continuously change t, the vector will continuously change as well, right? These are because all three of these are continuous functions, right? Cosine, the sinusoidal functions, and the polynomial, those are continuous functions. So if I continually change t now, I'm going to get a vector. If I make them all standard position vectors, then it will kind of sweep around, right? Sweep around in space. These vectors will sweep around in space. So another way, rather than thinking of this, the vector function as a set of vectors, you can also think of it as the set of points of the tips of those vectors when it's a standard position vector, right? So if you were to map out all those points, then what would you get? Yeah, you get it like what was a line in space? It was like a locus of point, like a string of points, right? You get a string of points. So this is what that vector function looks like as a curve in space, right? You take all those vectors as standard position vectors and let t continually increase, and it will, like a laser light show, it will show out a string of points. That's kind of hard to see now, but you get the idea. Okay, so so normally we think of vector functions as graphing as a curve in space, So this one's very complex. It's a nice first example because it's kind of cool. But the ones that you'll be working with will be a lot more simplistic, but this gives you the idea of it. So let's look at this one. What just happened? Oh, what just happened? Okay. So here's a more simplistic one that we're going to talk about here. So this is x equals t, y equals sine of 2t, and z equals 0.5 e to the t. And this is what this looks like. So a really important thing about understanding these and being able to graph them and work with them is the fact that because we're dealing with now basically 3 sets of 2 coordinates, right? X and y, x and z, and y and z. This function kind of has a face. It has different faces. So one face we can think about for this function is if you can look at x and y together. So if you just considered x and y together, x would be t, and y would be sine of 2t. And now we're back to a parametric function from Calc 2. And we should be able to kind of make heads or tails out of that, right? So what could you say about that parametric function right there? What do you notice? What's that?
Sine of 2x.
He went sine of 2x. Yeah, so this was a common thing we did in Calc 2. We would assign that x variable to be the parameter, and then it turns out then that now if x is t, then in this case y is sine of 2x. Which is a familiar sine function, right? Familiar sine function. So this vector function has y equals sine of 2x as one of its faces, meaning one of its perspectives. How can we see that perspective? We need to get rid of what? Z. If we eliminate z from the view of it, then we ought to see y equals sine 2x. So how are we going to look at this to eliminate z? Like a bird's eye view, like right up in the air, looking down on it. So if I take it like this, and we look straight down on it, and take z out of the view, what do you see? Sine 2x. Ooh. It's pretty cool, huh? But this is a key for understanding or trying to make sense of these functions, or if you had to sketch one, or if you saw a sketch and you had to kind of analyze it. You know, this is kind of looking at its different faces. Okay, so now what about x and z? What about the perspective of just looking at x and z? X equals t, z equals 1/2 e to the t. It's just what? 1/2 e to the, oh sorry, no, z equals 1/2 e to the x. Well, that's a easy pre-calculus function. That's our exponential function, 1/2 of the basic exponential function, right? How will that show up in what perspective? We got to get rid of y, right? So what should I do to get rid of y here? Yeah, look from the side, right? Look down the y-axis so we don't see y anymore, right? And then we'd expect to see, so if I want my x to be to the right and my z to be up, I'm going to do this, right? So now my x is to the right and my z is up, and then what do we see? Y equals 1/2 e to the x. Okay, and so then what about y and z? Y equals sine 2t, and z equals 1/2 e to the t. What's that? Who knows, right? This is complicated. This is not simple, right? Not simple. So, but we can easily find out what that function looks like by doing what? Look down the x-axis. So what does that look like if we look right down the x-axis?
2n or 2ln sine of 2t.
So basically what happens here, as z is, for lower values of z, it's going to fluctuate rapidly, but then as z increases, this is going to take over. So for low values of z, this is more apparent, right? It's going to be oscillating. And for high values of z, this is going to be more apparent because it's going to dwarf the oscillating factor. So I could zoom out here. I'm not showing enough of it here. So just like with parametric functions, since your domain is in t, so I can show a bigger range of t here. So for instance, I could show here, say, I will try from -6 to 10 and see what happens there. So they're showing more of it here, zoomed out. So this is the YZ perspective, this kind of weird curve that's a cross between sine and exponential, where you see more of the fluctuations of the sinusoid down here for lower values of z, and then you see the exponential taking over, just cruises up. And you see less of sine up for greater values of z. But then all three, this is what it looks like in all three, looking at all three dimensions, okay? So this idea of looking at, so what I called faces is really what's called projections. Projections of the curve into planes. So the projection into the xy plane we saw was what you get when you just consider the x and y coordinates, right? So the projection into the xy plane was y equals sine 2x. And I'd have to get this just right to get that to work over there. Yeah, so I'd have to, so it's because we're looking at an angle, we can't get it, but so you got the idea there. All right, and then the projection into the what, xz plane was this one? No, it was this one. There we go. Projection in the xz plane is the z equals 1/2 e to the x, and then projection in the yz plane was that other kind of more unfamiliar curve that we saw. So working with these projections is going to be really helpful for sketching, for understanding these vector functions. Okay, plus algebra. Oh, and then also another. So these are kind of key points to sketching and understanding these. Another thing is some curves that live on surfaces. So when you do the math, when you do the math to eliminate t, you may get a surface, right? Because you'll get an equation. You know, eliminating t would give you an equation of x, y, and z. We know equations of x, y, and z are surfaces. So the vector function doesn't give you all the points on that surface, but what that's telling you is that all the points on the curve are on that surface. So the curve lives on that surface. Okay, so let's see examples of that. So best I put you to work so you have enough time here. We got 12 minutes left. So see what you can do on these while I take attendance, and then, oh no, what happened? It shouldn't be that. Don't say. Okay, so I'm gonna race through these. So talk about them. So if you have two variables and one is cosine and the other is sine, we need to know what that is. So if you haven't learned this, you should have learned this in your career. But if you have not learned this in your career, today is your day. Today is your day. If you have two variables, one is assigned to cosine, the other is assigned to sine, how does that graph? Circle, right? That's the definition. Cosine, the definition of cosine is the x-coordinate, or the horizontal position on a circle, and by definition, sine is the y-coordinate, or a vertical position on a circle. So whenever you see cosine and sine paired between two variables, you're talking about a circle. And then if you add some constants, some scalar, if you scale one of those, then you get an ellipse, right? Okay, so this first one. So what does the y equals 0 mean? It's going to live in the xz plane. So you're going to get a circle of x and z living in the xz plane because x and z are sine and cosine, and y is 0. So there's no math to do here. If you see cosine and sine, boom, circle or ellipse. Okay, what about the next one? Again, here's the one where you look at it and you go, oh, I know what that is. What is it? It's a line. We know a point on that line. What's a point on that line? 1, 0, negative 2. And then how could we draw? Yeah, so we know the direction too. So we know that we have a vector, direction vector, and a point on the line. So it's just a line. That's the second one. So sketch the point in R3. From that point, sketch the vector 3, negative 1, 1. And then that will give you enough to just make a quick sketch of it. Okay, next one. What's the next one? It's a parabola, but if z equals 3, then this thing lives, the whole curve lives in the plane z equals 3, because every point's going to have a z coordinate of 3, so it's going to live in z equals 3. And what is living in z equals 3? Y equals x squared, right? This is the example I did before. So this is basically y equals x squared, living in the plane z equals 3. So sketch it as such. Okay, next one. Similar. Oh. What's the next one? So it lives in the plane x equals 2, and it's exponential function, right? Y or z equals e to the y, living in x equals 2. Where is x equals 2? In front of your page or in front of the screen, 2 units. So that it's going to live there. So there's that parabola y equals, or sorry, exponential function z equals e to the y, living in the plane x equals 2. So now these next ones are a little bit harder. And we'll pick it up from there. So this is the kind of thing where now we want to, so in the xy projection is what kind of thing? Ellipse, right? But now z increases with t. So you have an ellipse projected into x and y, but z increases with t. Spiral, elliptical spiral. So again, in the xy plane, you have an ellipse, but then z changes with t. So that thing just, as t increases, it just goes up with t. So that's called an elliptical spiral. We'll save the next one for next time. All right, so no written homework for Wednesday, just web work.